Welcome everyone to today's webinar. My name is Arya Hakimian, an application scientist here at C-Therm. And today we're looking at material testing for the development and design in both wearables and humanoid robotics. I'll be joined throughout today's session by two of my colleagues, Alex Mann, as well as Arya Sharostembiak. So we'll be talking about various areas of application from both thermal and mechanical testing perspectives as we go through today's content. Starting out with just a little bit of an introduction for those that may be new to C-Therm, kind of a little bit about who we are and what we do. So at C-Therm, we focus on thermal conductivity, specifically through the transient class of thermal measurements. Over today's session, we will be featuring a few of the different methods that we provide. But overall, the goal here and what we really try to demonstrate is simplifying the thermal conductivity measurement testing for the materials of tomorrow. And we do this again through the advancement of transient-based approaches. Primarily here on our core instrument, which is called Trident. This brings together four the most prominent methods in transient thermal conductivity analysis. Each one of these methods, of course, is designed to address specific samples, maybe certain testing conditions of interest. You will see as we go through, there can be certainly areas where more than one method is appropriate, but ultimately there are many where a dedicated device or dedicated approach really makes the most sense. But with Trident, you get this multi-method approach. And the idea behind this design really stems from a quote that we like from Abraham Maslow. See here, when all you have is a hammer, everything looks like a nail. And this is one, area where we can see if you try to take a good method of measurement, but just apply it in an area it wasn't designed for, that's where you're going to be more prone to getting poor data. So again, with Trident, it gives you more of a toolbox approach to really best address the task at hand. So for those that may be, again, maybe new to thermal conductivity or maybe just looking for some refresher materials, today's webinar will certainly go over a lot. But if you're looking for more like high-level information on the different methods, kind of seeing what options exist in industry, we do have a very comprehensive method selection guide. This was actually recently updated towards the end of last year. So great free resource to take advantage of if you're looking to maybe, again, learn a little bit more, kind of freshen up. Definitely would recommend pointing you towards this document. So as I mentioned, I'll be focusing primarily on the thermal conductivity side of things here today, but we do represent Rigaku for their thermal analysis line in North America, as well as Metrovib for their line of DMAs. And this is where my colleagues, Alex and Arya, will be coming in to speak to within these product lines capabilities and the relevancy of today's topic. I will also just mention that for those, potentially looking at, getting measurements done, we do offer a full service testing of all the core instruments from Trident, as well as our partner methods as well. So, as you're kind of digesting the information we're presenting here today, if you were interested in maybe running some measurements, looking for a group to do that for you, thermal analysis labs, it would be certainly capable to assist. All right, so jumping into today's topic, wearables and humanoid robotics. Some of the key topics that we'll be looking at here, and of course the relevancy to the material testing, we can look at user safety and the overall bio interface that occurs, of course, in, wearables, whether that's like a VR headset or a smartwatch, how those materials are interacting with the human body that they're in contact with. That can introduce different considerations around material performance and safety. Certainly something we'll be looking at throughout today's content. Overall system performance, with any of these advanced systems, the thermal heat that's being generated at some of these with these components, if that isn't effectively managed, this can lead to significant performance issues. This where you can get, for example, a VR headset, drops in frame rate, and it kind of gives you that stuttering effect, and that can lead to, a perceived motion sickness based on the poor performance. When we look at robotics, of course, if some of those components aren't, or if they're overheating, how is that going to impact what it's supposed to do, whether it's an arm that's flexing back and forth or whatever that may be. And then another big part that we'll be looking at is overall just material integrity and longevity. A lot of these components, whether they're exposed to cyclical loading, or, high frequency movements as that material ages and goes through some of these processes, what are your safety thresholds? How do we quantify how well this material is going to be able to perform over a long period of time under these kind of repeated conditions? So these will be some common themes spread out through today's session. If I was to really summarize or bulk them up together, wearables, we're going to talk a lot about user comfort and immersion. The thermal risks, of course, on that interaction with the component human interface. Skin burns, different types of sickness, again, VR sickness, things of that sort. And from the human robotics side, mostly looking at operational runtime, dynamic motion that is occurring here, and your overall thermal risks around the power systems and different failure modes, and the joints and the limbs and the actuators and things of that sort. So that's kind of setting up today's talk here. I'm going to start with a few little bits of a few examples here. I was looking into VR headsets. I've used these before, they're fun to play around with, but looking at it from a performance and comfort perspective, you can look at the overall design of these, somewhat straightforward when you think about it. You have that front housing, which is where of course, the electronics and everything is seated in. This is going to be your primary area where heat management can be a key consideration. This is surrounded by an outer shell. Oftentimes these are, airflow constricted. So there's, you're working in a confined space. How do we manage the heat that's building up inside of that casing? Things of that sort. Now, if you flip it around, of course, on the inside, this is where your lenses and displays are. Oftentimes, there'll be quite low thermal tolerances here. Thermal management perspective, but also like the materials involved, what happens to them, fundamentally changing shape or form. This is something we obviously want to avoid. We'll have some content presented on that. And then a big one when we talk about comfort, of course, is these are sitting on your face, right? So, this facial foam layer, this interface, which basically, seats around your forehead and on your cheeks. How does that feel? If you're putting it on and, playing around with some VR for, 20, 30 minutes, what is that compared to if you wanted to, have a longer session and you're in there for 2 or 3 hours? Like, how is that comfort aspect being taken into account? So an interesting point that or kind of an issue I've seen pop up with some VR headsets is what's known as forehead furnace. So this is actually when you get undesired heat accumulation at the interface. And again, that could be potentially building up from at the padding, but heating up from the actual core of the display unit itself. So, of course, without having heat dissipation pathways, this can lead to discomfort. And, a common theme here is this forehead furnace, which is, a low-grade potential burn. Obviously, all things that you're not going to want to have integrated into your product. Also, on the VR side of things, you can look at the certain, let's call them stability thresholds, where even small increases in temperature can really disrupt the overall performance of these systems. You're getting, your GPU and CPU components, the different like lag and latency that can build up. How that impacts the overall performance is, of course, something we want to be able to mitigate. So that being said, those different kind of areas and, kind of using the VR headset as our example leads us into thermal conductivity, because when we're looking to quantify performance here, thermal conductivity is really describing how well these materials are going to be able to transfer or move heat through the systems. So as we go through these next few sections, we'll be very much thermal conductivity focused. And there's an interesting paper here. This is from, I believe it's from this year, but looking at improving thermal conductivity of silicones. These types of silicones may be involved in some of these like smartwatches or, again, VR components. So this was a study here looking at really addressing the challenge that, silicone is in many of these portable devices, wearables, but they have limited base heat dissipation. And this isn't necessarily new specific to this area, but how groups are addressing this is through the use of additives and fillers, right? So you can see in this study here, just kind of quickly jumping into the results that they found by adding this form of copper nanowires into their system, different weight loadings, you're able to tweak and enhance that overall thermal conductivity, which is, of course, going to lead to better heat dissipation pathways. This was some data that was collected using the MTPS method, by the way. Now, interestingly, focusing just on the thermal side is one aspect, but they actually noted that within this study, they achieved that increase in thermal performance, but also maintain its desired mechanical properties, which in this case was the overall flexibility. So my colleagues will be kind of talking about some of those aspects as it plays a role into the larger systems that we're looking at here today. That's just one kind of little example there. Now, as we look at, these systems, the thermal and dimensional response in wearables, there's a lot of things to focus on. As these materials, like, are you integrating the material to dissipate heat? Certain applications where you're looking to actually maybe have some, if the material stores too much energy, what happens to the dimensional changes? Again, in a wearable system, is that going to result in deformations or, potentially, resulting in increases surface temperature, things of that sort. Now, as you go through these different areas, so whether it's a smartwatch or a VR system, whatever that may be, again, the comfort driven design requirements become really important here. And talking about where some of these can come up outside of just thermal conductivity, I'm going to pass it over to my colleague Alex to talk us through some of how Rigaku's product lines and what some of their measurements can tell us about this type of performance.
Thanks, Arya. So to start off, I'm just going to introduce the thermal analysis line real quick, just so we know what we're working with and what tools we have at our disposal. So the main three are the DSC, differential scanning calorimetry. We have the STA, which is the simultaneous thermal analysis, also known as the TGA DSC. And lastly, we have the TMA, the thermomechanical analysis. Rigaku is mostly known as a large XRD company. However, they do have a very proficient and robust thermal analysis line. So what measures what? We'll start off with the simplest, which is DSC. This measures energy, at what temperature something occurs at, how much enthalpy, things such as melting, crystallization, phase transitions, et cetera, et cetera. One thing that this does not do mass change. That's where we move into the STA or the TGA DSC category. This one, now we couple the mass change or loss along with our energy. So whenever we see an energetic event, we can easily determine if it's something like a melt, which has no mass change, or an oxidation, which gains, or a combustion or decomposition, which loses some. Lastly is the TMA, which concerns with a thermal expansion. So this one is great for CTE, it's the most popular feature, but you can also do glass transitions, softening point, any shrink by sintering, as well as solid-solid phase transitions can be detected by this method as well. So the first example we're going to look at for wearables is the DSC of a PCM, which is imbued in a textile. So a phase change material, or a PCM, is essentially something that melts within a desired temperature range. And then during this melt, it actually pauses the temperature. So this can be used to keep something cold or stop something from overheating. So for example, for a regular plastic, the specific heat capacity is around 1 to 2 joules per gram Kelvin. So as we keep applying heat, the temperature is going to continuously rise. Meanwhile, if it hits something like a melt, the energy is going to be around 150 joules per kilogram, or sorry, joules per gram. And when it hits this melt, the temperature pauses. So instead of using the energy to heat up by something like specific heat capacity, now all the energy is being used to turn from solid to a liquid. So we strategically place these melts at temperatures where we want to pause our temperature. So here, this is an example, a paper by Nejman and al. And what they did was they infused textiles with micro-encapsulated phase change material. As we can see here on the right, we have a traditional woven textile and a traditional woven textile, which has had PCM infused into it. These specific PCM they used was actually an acrylic paste that contained these microcapsules, which contained the PCM. So it was 20% for one of the sample and 40% for another of the sample. So we can see here on the DSC plot, um, we have cooling. We can see the exothermic reaction, which is the crystallization. And then on the heating, we can see the melting, which is an endothermic reaction. The results state that P20 had a very narrow area. So the temperature range was very narrow. And then for the P40, it was a little bit wider. And although that the P40 had, twice as much PCM, the actual enthalpy of the reaction was only about 30 to 40% more. So what the takeaway from this is that you don't just load your fabric full of as much PCM as possible. There is actually an optimal amount, which you need to determine by DSC. Now, how this applies in wearables, this is a great example for something like a VR headset strap or a watch or a brace or something where it's connected to you and you don't want it to overheat and cause discomfort. You want it to pause at a temperature that is close to that of body temperature. So for this example, we can see that the phase change occurs strategically around the 26 to 30 degrees Celsius, which is what would be comfortable for body temperature. Moving on, we have the TMA of a moist fabric for wearables. So this is some TMA data that was collected using two special attachments for the TMA. The first is a tensile loading attachment, which allows you to take the expansion of fibers or a thin film, or in this case, a fabric. And second is a humidity generator. So the humidity portion is really important because we want to test our materials in an environment that replicates their actual use. We don't want to test in a vacuum. So as we can see here on the chart, we held this at room temperature. There was no actual temperature increase, but what we did instead was we increased the levels of RH inside the feed gas, starting off at 0% RH, then moving all the way up to 80% relative humidity. So we have two materials, silk and polyester, silk being natural, polyester being synthetic. We see that the silk expands much, much more than the polyester whenever it is exposed to moisture. So an example for watch straps, bionics, braces, headsets, or prosthetics, getting them wet by either sweat, rain, or just humidity, it'll cause the fabric to expand. Or it's the opposite. If you're drying it, it'll shrink. So we don't want essentially a strap or something that's securing this wearable to you to either be loose and then potentially fall off or shake around, causing discomfort, or you don't want to shrink and potentially cut off circulation or cause irritation. So I'm going to pass it back to Arya.
Perfect. Yeah, so jumping back in, you were talking about a lot of, aspects in terms of comfort. So in terms of thermal comfort, we mentioned, thermal conductivity kind of regulating how much heat's actually building up. But when we want to talk about that, perceived skin to material contact feeling, whether it's warm or cool to the touch, this is another area where it's a related property, but more so focused on what we call thermal effusivity. And understanding how this plays an important role in terms of a performance metric for a lot of these wearables. Effusivity is very largely used in different apparel companies, for clothing, fabrics, whatever that may be. Any type of product really that's coming in contact with the human body. Thermal effusivity really describes the ability to exchange heat with another body in contact. So, the simple example here is, your hand touching some material or the shirt on your body or again, the VR headset on your face. So thermal effusivity and conductivity, these are related properties. You can see that through the kind of equations here. But specifically focusing on where this comes up, effusivity being used as, of course, a benchmark for performance in terms of that perceived feel and comfort. There's been many studies that look at, how this actually correlates. Previously, a lot of, how this was done before was based on touch panels. So like, does this feel warm or does this feel cool? But using effusivity, measurements, this can provide more of a really a quantified way of doing this, less subjective to what might be perceived in touch panel studies. And again, like, these kind of large groupings here, you can see metals, polymers, woods that perceive feel scales based on the increases in effusivity. But again, you can use this for a variety of applications, even within just a variety of textiles, even. So again, ones that are more warmer feeling versus cooler feeling to the touch. This is effusivity has really made its way into, material selection, also in like consumer marketing, different areas, different industries, effusivity kind of showing that higher effusivity values, keep you cool. This is something that we've seen across a variety of different applications, but certainly would have quite a lot of relevance here to wearables as well. So as a quick, summary here on what we just discussed with wearables, really thermal conductivity, that's going to be your core value output when we're talking about how efficiently heat is, spread or removed from a generating component. This is really a primary benchmark of performance that a lot of folks are going to be, of course, interested in. Thermal effusivity more so governs that heat exchange within the skin, driving that perceived feel of warmth or coolness. Um, Calorimetry style measurements, your DSCs, whether you're looking at heat capacity or phase change behavior. This is really looking at, again, how much heat the material can absorb and at what temperatures. And then lastly, CT or CHE determine the fit of, let's say, the wearable based on, the expansion or contraction that is observed. So as you can see, this, just looking at, wearables in and of itself, there's a variety of considerations here. No one property is, I would say, more important than the other. It really becomes a holistic approach to designing these products, again, with not only performance and safety, but comfort in mind as well. Now, switching into some of like the robotics, I was looking up some kind of interesting, seeing like what's going on in the world today with robotics. I'm not sure if anyone caught the Grammys there a few weeks back, but this Neo from 1X, this actually, if you were watching, kind of showed up in the Grammy Awards ceremony, or I believe maybe it was the after party, like actually greeting guests, serving drinks, taking pictures. So, when you think about like where are we at in the stages of development, there are some companies that are really, we're really pushing the advancement of these types of, robotic systems out there. And of course, with that, the design and the push to brings these products to market, what's going on in the back end in terms of optimizing their performance. Some other news, if again, this was, I think, announced the other week, Tesla is actually doing a big shift in some of their main production facilities, actually kind of halting production of some of the Model S and X systems in favor of really focusing on the Optimus Gen 3 line of robotic systems. I believe I saw they were targeting to have a 1 million robot per year output from the Fremont plant alone. So there's clearly a big, focus and drive going into these systems. But with that comes a lot of course, design, optimization, which revolves around material testing. So when we look at humanoid robotics, these are complex systems. You're working with defined form factors and spaces. Obviously, as with every electronic system out there nowadays, we're trying to increase that higher power density. And really looking at an important factor is how are those thermal management considerations being addressed? Because this is, whether it's robotics, EV vehicles, or, portable electronics, thermal management is going to be front and center to a lot of these considerations around, of course, the overall performance, utility, and the safety of these devices and systems. So looking at a few different kind of breaking down some components here, the processors, these would be, the onboard components that are really what's going to be, call it the brain of the system here. During operation, these thermal loads need to be controlled because, of course, if you don't address that, that's where you're going to have really breakdowns in performance and safety issues. So whenever we talk about thermal management of any type of processing component, thermal interface materials really become, front and center in the discussion as one of the key components that are being used to address some of these concerns. Now, when we look at thermal interface materials, these can take a variety of different types, whether it's greases, pads, adhesives, whatever that may be, but they all act essentially to fill the microscopic air voids that are present between your heat generating component and your heat cooling device. So in terms of optimizing these materials, we want to make sure they are very consistent and uniform, but also have a certain thermal conductivity performance metric to establish the desired transfer between those two. So these are, again, acting as the way of improving the heat transfer between the components. Thermal conductivity is a very critical component. If you look at like the technical data sheet for most thermal interface materials, thermal conductivity is front and center there as a key metric of consideration. But I want to take a look again at fillers here. So we mentioned that in kind of that first example for wearables, but in TIMS too, like adding fillers and the quality of the filler inside of the material is really what's going to be used to tailor that specific performance value of interest. But whenever we talk about adding fillers into a material, there's some things to keep in mind. One is, how is that filler behaving? In a non-ideal scenario, you could potentially experience agglomeration or sedimentation of the filler, essentially or a lack of consistency in that overall distribution. So what happens in these scenarios? Well, from a material perspective, this type of non-uniformity will result in overall decreases in performance, potential safety risks even. So it's something from a manufacturing side is we want to mitigate. But from a testing perspective, this can also introduce different levels of bias or errors in the measurement depending on which methods are used. We're not like we won't be going into all the nitty-gritty of each measurement and how they function, but different methods will have different, let's say, directionalities, different evaluated volumes. So if you have a lack of material consistency, what's being read from your measurements can be impacted by this. So we have to have a way of, understanding if this is actually going on in our system or not. And one of the really, I'd say, strong use cases of our MTPS is for this first example here called thermal mapping. Now, this isn't unique to robotics or wearables, but again, any type of material where there is a concern around consistency, this type of test, this type of thermal mapping can really provide a lot of insight. And what do I mean by thermal mapping? So let's say you had a sample. This one here, we can see just by looking at it, very non-uniform in its dispersion. But what if we couldn't tell that just by looking at it? What if it was an opaque material or we weren't able to visibly pick up on this? Well, what we can do with the MTPS, so the MTPS is a single-sided sensor with about an active area of around 18 millimeters. So what we can do is if you have a piece, like a larger disc, let's say, you can actually take the sensor and place it at these discrete locations and very quickly get an understanding of the localized thermal performance of that material. And as we can see here, there's no surprise that the different test locations resulted in some, quite significantly different results. But this type of measurement is really, again, possible because of the single-sided nature as well as the directional control that the MTPS has. So anytime, again, whether it's a filled system like this, any type of material where there's a consistency concern, where you're looking to do some of this mapping, this is something where the MTPS can certainly provide some benefits. So this helps you, of course, iterate whether you're in that early R&D development stage to pick up on some of these issues faster, or even if you're later on down the line in QA QC applications and you're just looking to very quantify that whatever you've designed is behaving as intended. This is certainly where the MTPS can really come into play. Now, of course, there are a variety of other techniques for measuring thermal conductivity, and when we look at TIMS, I wanted to also reference the more traditional flex TPS or transient plane source. So the transient plane source seen here, again, this is a different design, still one that is available in the Trident system. And where it really comes into play is more if you're looking for, I'll say, technical data sheet validation. You've gone through the development and you're looking to associate a performance metric to your sample. The hot disk transient method, TPS, ISO, these refer to the same style sensor. You can kind of see that here. So if ever you're looking at, comparing against maybe some material specs or you're looking to put your own spec out there, this type of approach is one that's very commonly used for thermal interface materials. You also get access to some unique capabilities if you want to go past just bulk materials, looking at thinner samples, anisotropic materials, thin films even. So the TPS really provides a nice framework for testing some of these material types. Now, when we look at TIMs, and any kind of a way that the TPS can really be utilized here is TIMs are of a very strong compression dependency to the effective thermal conductivity. And of course, in like a robotic assembly where you maybe have very like dynamic moving parts, if that TIM isn't in a static position, how will a change in load or compression on that material impact the effective results? So understanding the thermal conductivity under different compression loads can often be quite important in some of these dynamic systems. This is some data that is from an application highlight that's available on our website, but it looks at two different types of TIMs. One was a silicone, one was a non-silicone based TIM, but looking at adding increased amounts of applied force load, which resulted in a different, percent deflection within the material. But as you can see, you see this notable increase or net increase as a function of applied load, but different extents. So the specific material that you're working with, depending on what the base material is, how compressible it is, what fillers are involved, this is where you would be able to really draw some stronger conclusions of the overall performance by testing them under different environments or different conditions. Um, Now, with TIMS, there's, of course, another option that exists for characterization, and it is the TIM tester. Now, this isn't a device or a method, I'll say, that's available on our Trident platform, but it is an option that is very geared towards TIMS. We've actually recently acquired a ZFW TIM tester in our thermal analysis group, and this is a really nice option that opens up the door for conformance to the D5470 ASTM testing standard, which is again another one that is commonly used in technical data sheet validation. So, if you're looking to take this approach, different industries, different groups have their preferences, but this is another strong tool to look at, especially in terms of TIM testing. And it's more than just thermal conductivity. Interestingly, with the TIM tester, you can look at things like contact resistance effects, bond line thickness, delamination testing. And I want to kind of focus on this example because, again, with the same idea, if you have a dynamically moving system where those parts are not static, over time, what happens if they start to debond? How is that impacting your overall performance? And this is actually a really unique capability that you can test with a TIM tester. So, again, as it relates to robotics, with you have these more dynamic, repeated motions, even like cycling performance, how that interface contact may look at the beginning may change over time. And understanding where those thresholds are, of course, you can build in that extra wiggle room or that space to help accommodate that so it doesn't, detrimentally harm the system over longer durations. So this type of delamination testing is, something, again, you would look something similar like this. As you change, as the gap increases, the force will reach a peak load, and then you'll see this big drop off. So if we were looking at something like this and you see a clear delamination event, what that can tell you about is, how that material will end up performing under those different conditions. And quantifying the overall thermal performance of these systems under those different states can sometimes be really important to know, especially if you're trying to establish where those thresholds or limits are and where we, of course, need to bake in some protection to avoid. So again, whether you're looking at TIMS from a internal R&D development stage or technical datasheet certification, MTPS really comes in for that unique capability with thermal mapping. Both the TPS and the TIM tester have very relevant ASTM and ISO standards for technical datasheet validation, but depending on potentially preference or what the required standard is, that would potentially dictate which is the most appropriate one to use in that scenario. Now, I also wanted to just mention that, we talked about effusivity earlier in the wearables, but in robotics, these materials are being designed. They're not just metal kinetic frames. As you saw the Neo robot at the Grammys, they have some type of coating or fabric or skin. something in contact that's covering that frame. So again, the idea of that perceived feel upon contact can be really important, especially if we're interacting with these humanoid robotics. How is that going to impact your perceived the quality of the system or the comfort? Imagine shaking the robot's hand if it was cold metal versus something more warmer feeling. And again, this really comes back to that thermal effusivity side of things. Um, I will just kind of highlight that if you are looking specifically at textiles characterization in this space, ASTM D7984, which utilizes the MTBS, is the main method for this type of characterization. MTBS is actually the only sensor type method that conforms to this standard. So if you were looking to gain some more information on MTBS and textiles testing, I just kind of threw these up. These are from some past webinars we've done, but these really kind of detail how effusivity and touch is related. This was some work that was done in collaboration with the University of Oregon. We did a study together with them. Kind of just leaving the reference here on screen if you wanted to check this out on your own. Also, you can imagine, I know Alex mentioned, the consideration of moisture, saturation in textiles and the expansion and contraction. Well, a dry versus a saturated textile will also have a different outputted performance. So how does that come into play? So this was a webinar we did with the University of Alberta, which talked about that aspect. So if you want to learn a little bit more about the textile specific use cases, there's I would say quite a treasure trove of data and past content that really goes into that in further detail. All right, and at this point, I'll pass it back to Alex to kind of walk us through some of the other products here from Rigaku as it relates to robotics.
Thanks, Aria. Very insightful. So now we're going to look back at thermal analysis, but more for the robot theme. So starting off with some DSC and robotics. As we previously went over, DSC can be used to quantify the exact energy of a thermal event, as well as the temperatures that it begins and starts at. Some examples of this are the specific heat capacity, how much a set amount of an object or material can hold before the temperature starts to increase or decrease. The melting point, you can do curing studies to determine energy of cure, what temperature, as well as you can take parts that have already been cured and determine if they are fully cured, what the exact degree of curing in percentage. Look at crystallization of polymers. So is it as crystalline as you want it to be, or is it more amorphous? This affects properties such as the transparency, the flexibility. So if you're looking at an LED screen or any other parts. We, of course, have the glass transition, which is very important for, is your material glassy and stiff? Is it rubbery? As well as phase transition. Is it body-centered cubic or is it face-centered cubic? And how does that affect the properties? What temperature does this transition happen at? All things need to be considered. And the last one is reversible/irreversible. So all of these are really important for your design. So you need to know when these happen, if they happen, and stuff like that. So this is an application for service robotics and prosthetics. This was a nitinol skeletal framework hand designed by Lee et al. So what this does is it mimics the full carpal and metacarpal anatomy of the human hand. So it just helps with, grasping objects and creating a robot with a hand that can do what the human hands do. So it actually employs the use of nitinol, which is a nickel titanium alloy that exhibits shape memory and superelasticity. So nitinol is actually fairly elastic for an alloy. In its superelastic phase, it has a deformation that can be anywhere from 8 to 10% before it can snap back to its normal rest position. So what they found was using this nitinol for the framework, they could get a palm deformation of around 28%, which is the exact amount that a normal human would have. And although the palm deformation was matched, actually the payload capacity of this hand was twice that of human capacity. So this is actually a DSC view of a run of nitinol. So we can see during a heating and a cooling cycle, there are 6 points that have been labeled. When working with nitinol, it is important to know all of these points. So we have the start, the peak, and the finish of the martensite and the austenite phase transitions. So in the austenite phase, this is where the alloy exhibits its superelastic properties. So this is on the hot side or the higher temperature, also known as the parent phase. So in this phase, this is where you can deform it up to 8 to 10% and it'll immediately snap back when the force is released. Then in the daughter phase or the martensite phase, this is where we get the shape memory effect. So we set you know, the neutral phase in the austenite, and then we cool it down to the martensite. Then when it's in the martensite, it's actually very flexible and malleable. We can bend it to any shape we like. And then when we heat it back up to the austenite, it'll snap back to our predetermined neutral phase. And this is what's known as the phase memory effect. And this can be useful in robotics because we can have the hand or any other part be deformed. And then when we want to take it back to its initial resting state or we want to reset it, we can heat it up and it'll snap back for its shape memory effect. Now, as we can see here, sorry, I'm going to go back here for a sec. As we can see here, the temperature this occurs at is a little high, anywhere between 40 to 60 degrees Celsius. This temperature can actually change based on the composition of the ratio of nickel and titanium. And also, instead of having to heat this up, what we can actually do is we can apply a current to, a nitinol wire in order to heat it up. So we can keep, the rest of the robot at a room temperature and just apply current to this exoskeleton or to any other nitinol parts. Next, we're moving on to STA. So this, again, as mentioned, it combines the mass change and the DSC, so the energy and mass change. So people always ask me, if STA can do DSC, what's the point of getting a regular DSC? And it is a pretty good question. And my answer to that is kind of how it's built and what it's meant for. So for the STA, in order to actually capture the mass change, it needs to be either suspended from the top. The sensor needs to be suspended from the top or on a rod coming in from the bottom or side. And then on a DSC, the floor of the furnace is the actual sensor. So what this does, it affects the stability of the signal. So if you're looking for something like a specific heat capacity or a glass transition, which is really needed you need to measure the baseline to get this, the pure DSC excels a lot more. Something else to consider is that in STA, you're getting a mass change, which can come by, reduction, it can come by oxygen for oxidation, or just plain old thermal decomposition. And some of these occur at really high temperatures. So the sensor is really robust in order to withstand all of these harsh events. In doing this, the sensor itself kind of loses a little bit of sensitivity. So again, we get this robust sensor for STA, but the sensitivity isn't as much as if we were to do pure DSC, which does stay a little bit lower. One last thing is that the STA, again, we're measuring mass loss. Not a lot of that happens at subambient temperatures. So the DSC itself really shines when we're going down to -40, -90, or even -180 degrees Celsius. So how does this apply to humanoid robotics? Well, it's commonly used to evaluate the thermal stability of polymers. So, when we take it up to a temperature that's above what we want, how long is it going to stay before we start to see damage, before it starts to degrade? Next is we can look at filler or the reinforcement content. So this is, again, if we're using carbon fiber, if we're using carbon black, or any inorganic filler in order to strengthen a polymer within a composite. The next is the actual degradation temperature. So if we heat it up, at what point does our polymer either vaporize or just suddenly decompose? Lastly, again, going back to humidity, STA, because it does measure mass change, we can do moisture uptake to see how your polymer will gain or lose weight under dry or humid environments. Here's an example of a carbon fiber reinforced polymer test using the STA. So this test right here was crafted in order to determine the three components. The first would being the polymer. So what happens here is we ramp up the temperature in a nitrogen environment. So as the temperature increases, the polymer, it thermally decomposes. We lose all of it. So the first mass loss, we can determine that is entirely due to the polymer. So we have 24% of polymer. And then carbon fiber, because it's pure carbon, can't actually decompose under nitrogen because it has no pathway. It needs the oxygen from air in order to become carbon dioxide. So after holding it at 1,000 degrees Celsius, we switch all of a sudden to air and we get an instant burn off of the carbon fiber. So we can see here that the carbon fiber in this carbon fiber reinforced polymer by mass is about 75%. Now, if you're doing some math, you might realize that there's around 0.75% of the mass that's missing. This was actually due to inorganic contaminants. There were a little bit left over in the crucible. So this is important because you don't want high contaminants for something like a metal where it can actually induce, you know, electrical conductivity. You want your carbon fiber reinforced polymer to be stiff. You want to have a high strength to weight ratio. And in some applications, you want it to be non-electrically conductive. Next, we're going to look at some TMA in humanoid robotics. So right off the bat, robots have tight tolerances with a lot of moving parts. If there's unaccounted for expansion, it can cause, grinding, stress, unnecessary wear. Next, we have a lot of different materials going into these robots. We have some body that are made of titanium, aluminum. We have carbon fiber, just glass and optics and displays. We have, rubber and elastomers, as well as adhesives holding a lot of stuff together. And lastly, although the robot ideally, should be around room temperature, we do have external temperature fluctuations. Also, there's heat being generated within the system by motors, electronics, and also some of them have cooling systems. So we can have our cooling systems, our heating, and our ambient temperature all causing different temperature at different parts in the robot. So it really needs to be accounted for. So the importance of CTE, what happens if it's not factored into our designs? For some, we can get delamination if we have two things that are mated or stuck together. We can also get warping if we have two malleable things, metal, polymer, that are stuck together. And lastly, there's thermal shock. When we have brittle components like a ceramic or a glass and we change temperature too fast, it can just crack it or cause it to chip. We have a nice little image here of some warping due to heat, and our last image here would just be some ceramic thermal shock. So we're going to look at some TMA for some optics for some robotic vision system. So first and foremost, as mentioned, large temperature swings can cause cracks or chips because they are brittle. We also have to look at the lens and the housing it's in. If we have some different mix match and all of a sudden the lens becomes loose, it can move, it can shift, it can tilt, causing issues. Also, we have to look at the lens shape itself. We can have thickness increase or decrease. We have the actual diameter of the lens as well as the radius of the curve. This can affect the focal length. We can affect the focus. It can cause some drift. And lastly, it can cause some aberration. So all these can lead to either blurry images or, outright just not working. So as you can see here, this is Wang et al.'s robot. And on it, it not only has a LiDAR detector, but also two different cameras and interaction LED touch panel. So, there are very many optics and glass components on this robot. Next, we have some CTEs of some common optics and mounting material. This was taken from Doyle, Geinberg, and Michaels out of a optothermal analysis textbook. So not all lenses are very small CTE, and not all lenses or housing have high CTE. There's very, very many choices out there depending on what application you're using. But what you have to do is kind of match them. So as we can see here for fused silica, there's also the Invar, which can be used as a housing. For our BK7, we have titanium, which has a really close CTE. And then for FK54, we're kind of in between the middle of titanium and aluminum. And then as well for consideration, polymers and all a bunch of adhesive rubbers, they can have CTEs that are within the hundreds, so they expand a lot more. There's a lot to take into account. Here is an example of the TG and the softening of glass. Most like to think that glass has a very high TG and softening point crystallization. However, that's not always the case. Here we can see a chalcogenide glass. It's used a lot for infrared sensors. And as we can see here, it has a fairly large expansion compared to other glasses, and then a low TG. And then it starts to soften at 309 degrees Celsius. Although ideally, your robot wouldn't reach these ranges, but you still have to you have to do take in the account for the expansion. Yeah, so we spoke a lot about a lot of static applications. But now I'm going to pass it to Arya Steinbeck to give a little discussion about how we introduce repeated motions or dynamics into how we characterize our materials.
Yeah, well, thank you very much, Alex and Arya, for an insightful and informative presentation. So here, I'm going to talk about a mechanical behavior in robotic applications and humanoids. As Alex and Arya presented their slides about thermal analysis, it is also important to understand the mechanical behavior of materials through temperature and thermal analysis. I'm going to start my presentation with this statement that robotic systems are in nature not static. There are some static deformation. However, it is important to understand and consider that for different parts of robots and robotic systems, we have dynamic deformations, which can come from different resources, for example, for vibration, or when we're talking about humanoids, from joints or different movable parts. So this is very important to understand. The dynamic mechanical behavior for these applications. For example, a quick formula here, a dynamic Poisson ratio, is what we obtain through dynamic mechanical analysis, which is a dynamic mechanical test on different materials. For example, in the figure here, you can see different deformation mode with different direction of deformation and complex direction for deformation, basically increases the importance of understanding different direction for deformation. This is something that can be addressed using Poisson ratio. Specifically for dynamic applications, it is important to use a dynamic Poisson ratio since it is frequency dependent. In this slide, you can see our DMA, or dynamic mechanical analysis, can give us the results for modulus. We have it in two different demonstrations here, and G. E is the elastic modulus, and G is the shear modulus for the material. And this ratio, which is called dynamic Poisson ratio, is the key, and it's the bridge between shear deformation and elastic deformation, which is very important. Through this formula, which is obtained through a simple DMA test, you can basically fill the gap between different deformation modes, which can be used in simulations or other analysis. And I'm going to talk about later. But just for an introduction, this is why DMA, or dynamic mechanical analysis and mechanical behavior, is important in robotic applications and robotic systems. In the next slide, um, I'm going to introduce DMA. DMA stands for Dynamic Mechanical Analysis, and it is the most accurate technique for measuring the viscoelastic properties of materials. Viscoelastic properties are inherent to different materials, for example, polymers that are used quite often for robotic systems and robotic applications. A few bullet points I want to mention here, and we're going to go through, which DMA can help us with. First of all, glass transition temperature, which is one of the core values of DMA, filler dispersion, high frequency evaluation, simulation, as I mentioned before, and at the end, fatigue and failure analysis. Each of these points are very important, but before I go further, let's talk about DMA and how it works. As you can see, DMA has the sample clamped between two sample holders, one part on top and the other one on the bottom. The top part is static and the bottom part is dynamic and it's movable. And as you can see, there is a displacement or force applied, and the displacement or force as a result is being recorded. And in this test, we can understand the viscoelastic properties of the material. As you can see, there is a delay between the response and the force applied to the sample, which is called phase angle, and that is the reason behind viscoelastic properties of the material. And This information can be very useful for different application, and I'm going to explain from next slide. So first slide is going to be dedicated to glass transition temperature. And as you can see here on the right axis, we have E prime, which is elastic modulus and is more related to stiffness of the material. And for the next step, actually, I'm going to show you the formula that elastic modulus can be involved here. As you can see on the bottom right part, we can see E prime, which is storage modulus or elastic modulus, more assigned to stiffness, and this is the ability of material to store the energy um, and return it. The other parameter we have is E double prime or loss modulus, which is the ability of material to disperse the energy within the matrix. The ratio of loss modulus over storage modulus gives us the value of tan delta, which is very important in determination of glass transition temperature. Running a test across a temperature, for this case, for example, from minus 60 degrees C to 100 degrees C, we can see that there is a peak in the value of tan delta, and there's a drop in our storage modulus. So this is very anticipated for storage modulus to drop across the temperature since it is tightly related to stiffness. As you heat up your sample, the sample is going to become softer. However, the importance of a DMA test for glass transition temperature is the peak in tan delta. Tan delta, which is also known as damping factor, is the most accurate technique to understand glass transition temperature. So, as you probably know, glass transition is a mechanical relaxation that happens in a material. There are different methods to understand and measure glass transition temperature. However, there are some limitations. For example, one of them is the filler content for composite materials. People in different applications can use different filler content. And one of the reasons that DMA shines is that even with high filler content of material for composite, you can still measure the glass transition temperature. And as you could see in the previous slides, the frequency is important here, and having a frequency-aware measurement can play a crucial role for your material, since if the glass transition temperature is underestimated or overestimated, you can risk having premature failures in your system, and it can be a safety concern. So, as we're talking about capabilities of DMA here, I'm going to talk about the filler dispersion. Making composite materials, a very famous China and well-known issue with the materials and challenge of developing different composites is the filler dispersion. As you can see in the picture, for example, with having a poor dispersion of the filler within your polymer matrix, for example, as a composite, you can take some risk for a failure because one part of the material behaves like an advanced material, but the other part is very prone to failures, which can again face us safety challenges. There are different ways of evaluating dispersion within a matrix of a composite. However, they can be time consuming or not really cost effective. So DMA can provide a very simple tool, easy and fast measurement to understand and basically give you this capability to have a comparative tool to compare your dispersion between the samples. For example, on the left graph, as you can see, we have different fillers in PDMS. For example, titanium on the top. It was the composite was made through in situ um, um, preparation for the sample, and we also have silica on the bottom. So as you can see, the storage modules of the material starts dropping by increasing the strain value. And this is usually happens due to the filler to filler network. So if you have a well-dispersed sample, the filler to filler interaction and network is quite uniform throughout the matrix, and you see less of that pain effect or the drop in storage modulus. For example, on the left graph, you can see titania has a significant drop by increasing the strain. However, silica shows less of that drop, which means the filler network is more promising in that sample. And on the right-hand side, we have another example, which is the treated silica or non-treated silica. So the treatment that is done under a filler for different composite help the filler to disperse better. And as you can see, we can see the less of a drop in treated silica, which shows significant improvement in filler dispersion. And this test can take less than half an hour to run, and it gives you a very powerful tool to understand the dispersion of your filler in the material. Moving to the next slide, I am going to talk about high frequency mechanical performance. As I mentioned before, robotic systems and robots are inherently dealing with more dynamic mechanical deformations, and frequency is very important. As we talked about it, different frequency can shift the value of glass transition temperature. Which can affect the performance of the material. So this is very important to understand the frequency behavior of the material under deformation mode, because it can prevent failures or it can significantly boost the performance of the material under real world application conditions. So moving forward to the next slide, one of the tools that we can evaluate high frequency performance is time temperature superposition. And on the right-hand side, as we can see, there's Boltzmann principles of time temperature superposition. So this basically explains how lower temperature can simulate the high frequency behavior of the material, and how high temperature can simulate the low frequency behavior of the materials. Knowing that concept and applying through a mechanical test, we can have access to very high frequency results through modeling. So next slide shows you a simple time temperature superposition test. And as you can see, the data, the range of frequency we're getting for this test is quite significantly large. For example, from less than a millihertz all the way down to 10 to the power of 8 hertz, which is quite significant for us, especially for the applications like simulations. If you're working for simulation like FEAs through softwares like Abacus and other softwares, it really helps you to build a strong model for predicting the behavior of your materials. Or another application can be fitting the data for Prony series and build a strong Prony series. Because you have access to large range of frequencies. And it's different than typical DMA tests, because normally the DMA test can range something from 1 millihertz to 100 hertz or 200 hertz. However, this is orders of magnitude higher, so you have this advantage to build a stronger model, and validation of the model will be more promising. Moving forward, let's talk about fatigue analysis and failure analysis a little bit here. So the terminology here that we'll be using is crack nucleation. So basically, once you apply the deformation through cycles or repeated motions, which is more prominent in the robotic systems. Basically, the deformation is not really peak load, but it's a repetitive motion. When that starts happening, after a certain number of cycles, we see failures in the materials, and it is known as crack nucleation. And as you can see on the second picture, that the material starts showing a significant drop in storage modulus, which is again assigned to stiffness of the material. You can see the material is permanently deformed. This is what we call as crack nucleation. Basically, this is when the crack initiates in your sample, and your sample can be permanently deformed. So this really helps you to understand the failure of the sample when it starts, and you can schedule some predictive maintenance and lifetime estimation, which can be very useful, and it prevents safety hazard for your material and safety risks. However, moving forward, we're not going to be only focusing on when it starts, but also how it progresses through um, the cycles of deformation. So this is a very neat capability that Mitrovid DMA provides, and it's called crack growth module. So basically, this is a fatigue testing. However, it's one step after the failure starts. So this test is very interesting because you can also customize the deformation cycle that is happening. Either you can have sinusoidal waveform for deformation, impulse, triangle, or hover sign, or other customized deformation way for your material. And it's basically focusing on after failure. So the phases that you go from initiation of the failure all the way to the complete failure of the material. And it fills the gap for failure analysis. Next slide, I'm explaining here the different phases. For example, so this is the graph that you get from a crack growth test module. On the left-hand side, you can see the crack growth rate, which is nanometer per cycle. And on the x-axis, you can see tearing energy. And so basically what is happening here in zone one, basically there's no failure. It's material healthy performance. And from T0, we can see the crack initiates, and zone 3 is dedicated to crack propagation. So basically, the failure starts propagating through your sample, and zone 4 is essentially the failure zone where the material completely fails. These are some capabilities from simulation to giving you access to understand the glass transition temperature, failure analysis, and preventing failures that DMA can provide for different applications in robotic systems and different parts. That's it about my slides. Thank you for joining us, and I let Arya to walk you through the outro.
Awesome. Thanks, Arya. So, yes, folks, I know a little bit longer than usual here today, a lot of content to get through, but just wanted to say thank you for joining. Just going to go into a little bit of an outro, so go through this quite quick. But if you were looking for kind of additional resources, check out our website, past webinars, tech library, a lot of great content to find in there. I will just also mention that we do have some upcoming webinars scheduled for the month of March. March 12th, we'll be joined by a guest speaker from Lakehead University taking a look at aerogel cellulose composite testing in the insulation space. March 19th, with a partner in the UK, SciMed, looking at some of the innovations in thermal conductivity testing. And then later in the month, to wrap things up for March, we'll be looking at another joint webinar with Thermap Solutions, exploring thermal properties with frequency and time domain thermal reflectance. So if anything presented here today sparks some interest, maybe you want to learn a little bit more, we are certainly happy to schedule technical consultations, whether that's for the MT or for our Trident system, thermal conductivity, looking at Rigaku or the Metrovib series. So definitely feel free to reach out if you would like to maybe dive into some of these topics in a little bit more detail. If you like what you see and maybe you're just looking for some budgetary information, we do also can provide some free quotations. Again, just definitely reach out. Happy to set those up. If we need more information, we can, of course, get in touch and really kind of confirm what you're looking for and what would best suit the testing requirements of interest. I will just make note for anyone that is joining us from the academic sector, we do have an academic support program for our thermal conductivity instrumentation. You can see some of the information here on screen, but if you are reaching out and you are in a registered academic institution, please make note of that. We'll certainly be happy to provide this in the follow-up content. Lastly there, give us a follow on LinkedIn as well as subscribe to our YouTube channel. This is where we post everything from, upcoming webinars and events, application content, blog posts, videos, etc. So if you're looking to keep up to date with us, this is where it all goes first. And with that, that brings us to the official end here. Again, To the folks that joined for our session, thank you for being here with us today. To my colleagues, Arya and Alex, thank you for your contribution to today's session.